Section 19.6 is about the relationship between free energy and cell potential. So a positive standard cell potential and a negative standard Gibbs energy of reaction both mean that a reaction is spontaneous under standard conditions, that it will proceed in the forward direction under those conditions. But we can make a more precise relationship between Gibbs energy and potential. So that is that delta G is equal to negative NFE. That's under general conditions. And then of course under standard conditions we could just say it's delta G naught is equal to negative NFE naught. So what are the N and the F in these equations? N is equal to the number of electrons transferred. Okay, so this is one equation where you will want to balance the reaction in the cathode and the half reaction in the anode, and figure out exactly how many electrons are being transferred. Now I want to point out you don't have to get a complete balanced chemical reaction with all of the H pluses and waters or OH minuses, whether you're in acidic or basic conditions. For this number N, just looking at the charges and the number of electrons in both of those reactions and finding their least common multiple will be sufficient. All the H pluses and waters and OH minuses that you might do in those last steps of balancing a redox reaction, they won't affect the number of electrons, and so they're not relevant here. So that's N, and then F is a new constant. It's called Faraday's constant, named after Michael Faraday, and it is it's the charge of a mole of electrons. And so the SI unit for electrical charge is a coulomb, and the units for Faraday's constant will be coulomb per mole, and it is 96,485 coulombs per mole. Any in the Heights fans will find it easy to remember the value of Faraday's constant to at least 2 sig figs. Coulomb again is the unit of charge, and this is per mole for a mole of electrons. Over here we have units of moles and coulombs per mole, and then volts is the unit for potential. And so on the right hand side what we ultimately have is a coulomb volt, and a coulomb volt is actually equal to a joule. That's what makes SI units convenient and easy to work with, is that any units that can be derived from each other are usually derived from each other without any necessary conversion, which means everything over here is going to be in units of joules, and usually Gibbs energies are expressed in terms of kilojoules, and so we'll want to divide by 1,000 to do that conversion. And then also I tend to talk about Gibbs energies, enthalpies of reaction, entropies of reaction, etc. in terms of kilojoules per mole. And this is one case where it's better to just talk about it in terms of kilojoules. Now that per mole makes a lot of sense to me, especially when we're teaching these early thermodynamic topics, because you're going to be using them in the context of a dimensional analysis problem where you want to say so many moles of a reactant yield so many kilojoules, etc. But you'll notice that the units here work out to just be joules. There's no per mole. This per mole cancels out with the number of moles for N. And a lot of textbooks will just give Gibbs energies and entropies and enthalpies of reaction in terms of joules and kilojoules without the per mole. Or you can say that N is unitless and carry this per mole through, which is what I usually do. And I guess I'm just being overly transparent here in how my approach differs from at least some of the textbooks, and I believe your textbook as well, although now I'm second guessing myself. Under standard conditions, of course, we just add the knots, but we can find the, if we wanted to measure, say, the potential under non-standard conditions, we could figure out the Gibbs energy under those non-standard conditions as well. In other words, concentrations that aren't equal to 1 molar, pressures that aren't equal to 1 atmosphere. Okay, so let's consider that zinc copper cell that we were talking about in our last few lectures, right? Our sort of prototypical electrochemical cell. You may recall that has a standard cell potential equal to 1.10 volts. So can we find the standard Gibbs energy for this cell? And we can indeed. The delta G naught then is going to equal a negative. Now, we balanced this equation a few sections ago, but you can tell that the zinc is going to be oxidized to a 2+, the copper 2+ is going to be reduced to solid copper. That involves the exchange of 2 electrons. And then Faraday's constant, 96,485 coulombs per mole, times that cell potential of 1.10 volts. And that is going to give you a delta G naught equal to negative 212,000 joules per mole. Okay, or usually we express this in kilojoules, so negative 212 kilojoules per mole. And if that seems like a large magnitude negative delta G, well, electrochemical reactions are often very powerfully spontaneous or very strongly spontaneous. They'll have very negative delta G's of reaction. Where's my eraser? Here we go. So we'll leave those equations up there. But if we can relate standard cell potential to standard Gibbs energy, and we also know that delta G naught is equal to negative RT ln of K. Well, if these two things are both equal to the same Gibbs energy, then that means they're equal to each other. So E naught can be expressed different ways, but usually we say E naught is equal to RT over NF ln of K. So if we look at figure 19.8, this kind of summarizes how all of these values, the potential and the equilibrium constant and the Gibbs energy, are related to each other and how we can go back and forth between them. If we want to do a conversion between standard cell potential and standard Gibbs energy of reaction, then we'll use this. Delta G naught is equal to negative NF E naught. If we want to do a problem involving the equilibrium constant and the Gibbs free energy, then it's this. Delta G naught is equal to negative RT ln of K. And then if we want to do a problem that involves relating the standard potential to the equilibrium constant, sorry, I need to drag this down a bit, there we are, then we can use E naught is equal to RT over NF ln of K. So let's do one of those problems real quick. So can we use the standard cell potential for, again, that zinc copper voltaic cell to find its equilibrium constant? Well, that would be 1.10 volts is equal to, oh, and I forgot to write this in my notes, but the temperature appears here, and so of course the temperature will be relevant. Let's just assume room temperature, 298 Kelvin. So that R, remember this is R in the context not of gas laws, but of our thermodynamic equations. And so what we want is 8.314 joules per mole Kelvin times 298 Kelvin over N. Again, that's the number of electrons transferred for our zinc copper cell. That will be 2 moles, or 2 times Faraday's constant, which is 96,485 coulombs per mole. And that is all multiplied by the natural log of K. And so what you'll do is, I actually don't have the intermediate answer here, but the natural log of K will end up being equal to some number, which would be 1.1 times 2 times 96,000 divided by 8.314 divided by 298. And you'll notice that your kelvins cancel, your moles cancel, and your joules will cancel with the coulomb volt, and so that number is going to be unitless. And in order to get rid of the ln of K, then we're going to have to raise e to the power of both sides. And maybe it's worth me actually really quickly finding that intermediate answer. So give me a sec. Okay. Sorry, it's taking me a minute to get it set up. Alright, so what do we need? We've got 1.1 times 2 times 96,485 divided by 8.314 divided by 298. And that's going to be 85.675. So the natural log of K is equal to 85.675. Okay, one moment, I'll let you see that I've written on the board. And so I'll just raise e to that power to undo the natural log of K. So K is going to be equal to e raised to the power of 85.675. So let's double check, as long as I've got my calculator up. Let's double check that. So, 85.675. Yes, and I guess if we I don't know why I only gave myself one sig fig in my notes. You can see there my notes should be 1.62. So get rid of that. 1.62 times 10 to the 37th. A rather large number, not the biggest magnitude number we've seen yet. A lot of our solubility equilibrium constants, for example, are 10 to the negative 50, 10 to the negative 60, 10 to the negative 70. but it's definitely up there. So these are highly spontaneous reactions. Equilibrium lies very far toward the products, and that is the equilibrium constant from the standard cell potential.